So let's check it out, read it, draw a picture. Pilot flies in a straight path for an hour and 30 minutes. She then makes a course correction heading 10 degrees to the right of her original course and flies 2 hours in the new direction. She maintains a constant speed of 675 miles per hour. How far is she from her starting position? Okay, so let's see. Flies in a straight path for a while, then 10 degrees to the right of her current position. So I guess I'm going to make this picture vertical. So we start flying and we fly for a while. For how long? An hour and a half. So maybe let's say 1, 2, 3, 4 is an hour, and then 1, 2 is an hour and a half. So she gets to there. And then she changes direction 10 degrees to the right. Okay, so 10 degrees to the right. So that's not much of a change, right? So this is flying 10 degrees to the right. It's maybe like that much right there. I'll exaggerate a little bit and make it that much. And she does that for 2 hours, which is a little longer than that other line. So if I went up 1, 2, 3, 4, there's 1 hour. 1, 2, 3, 4 is 2 hours. And then I just kind of tilt that on a circle. So that maybe is around there-ish. And then we want to connect how far is this point there from where she started there. So we get this very narrow triangle right there. So what do we know? So here I tried to mark off an hour and a half, and over here I tried to mark off 2 hours at 675 miles per hour. So this side right here is 1.5 times 675, right? Hours times miles per hour gives me distance, rate times time. And this red one is going to be 2 hours. Oops, let's do that in red. 2 hours times that 675, right? Rate times time is going to give me that distance there. And what else do I know? I know that this angle right here, this skinny angle, that right there is the 10 degrees. And it is supplementary to this inner angle here. So that inner angle there inside the triangle has to be 170 degrees. So what we have is 2 line segments in a triangle with the angle between them, which is the law of cosines. So this opposite side, so let's maybe call these side B of my triangle. And this one right here could be side A. And we want to know that distance here, let's call that side C. So according to the law of cosines, C squared equals A squared plus B squared minus 2 times A times B times the cosine of the angle between them, which we just calculated. That's my angle C, or 170 degrees. And so C will be the square root of all of that. So we're going to have to make this calculation and that calculation and then plug them in. So I think let's do that on a calculator. And sure, I'll use GeoGebra here. So let's clear this stuff. All right, so my side A, I was calling that 1.5 times 675. And then side B was 2 times 675. And then C is going to be that crazy square root I just talked about. So shall I call it C equals? It doesn't matter. I'm just going to grab a square root. Let's see, basic square root. And then I just want my value A squared. I can just call it A squared plus B squared minus 2 times A times B. It's one thing I love about GeoGebra and Desmos, where I can name values and not worry about retyping them. times the cosine of the angle between, which was 170. And then I always like to double check degrees there, didn't change the answer. And so I get that distance in between if she went, let's see, 1,112.5 miles, followed by a slight 10-degree turn, and another 1,350 miles. Altogether, it should be a little less than those two combined, which it is. Good. 2,353.7. How many decimal places does this want? 2 decimal places, sure. 2,353.69. So again, once we draw that picture, we could see it was the law of cosines once we translated that 10-degree angle to the supplementary angle inside the triangle. And is there another way to calculate that? Not that I can think of at the moment.